All right, welcome to the AI Research Roundup. I'm Alex, and today is May 10th, 2025. Today, we're diving into an ICLR conference paper titled HiRA, Parameter Efficient Hadamard High-Rank Adaptation for Large Language Models, which was published just over 3.5 months ago. This paper addresses the challenge of efficiently adapting huge large language models to new tasks. You see, current methods like parameter-efficient fine-tuning, or PEFT, are key here. A common one is low-rank adaptation, or LoRA. LoRA works by making updates using components with a low rank, which is a sort of measure of their complexity, to save on computational resources. But this low rank can sometimes be too limiting. So this paper introduces a new technique called Hadamard high-rank adaptation, or HiRA. It cleverly uses what's known as a Hadamard product. That's basically an element-by-element multiplication of numerical grids to potentially create more complex and thus more expressive updates for the model without losing too much of that prized efficiency. Okay, so this first figure really visualizes a core idea. It compares the rank of the update parameters. These are the actual changes to the model's settings, often called delta W for the proposed Hadamard high-rank adaptation versus low-rank adaptation, and another method, LoRA. Along the bottom is R, that low-rank dimension controlling trainable complexity. What's striking is Hadamard high-rank adaptation. The solid blue line maintains a very high rank for its updates, near 2800. In contrast, low-rank adaptation's updates, the dotted orange line, have a rank tied to R, staying much lower. LoRA's updates, the green line, are higher than low-rank adaptations, but still well below Hadamard high-rank adaptations. This highlights how the new method achieves more expressive, high-rank changes. So knowing that Hadamard high-rank adaptation can make these more expressive changes, this next figure shows how standard low-rank adaptation performs on the Llama 3 to 8B model across several common-sense reasoning tasks. These are basically tests of everyday knowledge and reasoning. We see performance on the vertical axis plotted against that R value, the low rank dimension, along the bottom. Generally, as R increases, giving low rank adaptation more trainable complexity, the average performance, shown by the dashed black line, tends to improve across these different reasoning benchmarks. This provides a baseline for comparison. Building on that baseline, this next diagram really clarifies the how. At the top, low-rank adaptation. The new weights, W prime, are the original W0 plus an update, delta W. This delta W is from two low-rank matrices, L1 and L2, so its rank is limited by R. Now compare that to Hadamard high-rank adaptation below. Here, delta W is also added to W0, but it's formed by the Hadamard product of a low-rank matrix derived from A and B with the original pre-trained weights W0. This clever step allows delta W to achieve a much higher rank, effectively incorporating knowledge from those original weights. Alright, so this table now puts some hard numbers to these ideas. It's showing an accuracy comparison of different parameter-efficient fine-tuning methods, like prompt tuning and p-tuning, which both cleverly adjust model behavior by learning special input prefixes, alongside low-rank adaptation, DORA, a variant that fine-tunes update size and direction, MORA, which uses multiple low-rank updates, and of course, Hadamard high-rank adaptation. On the Llama 3 to 8B model for common-sense reasoning, Hadamard high-rank adaptation with R equals 32 reached an average accuracy of 86.72%, notably outperforming DORA. This really underscores its effectiveness. Alright, moving from reasoning, this table looks at open domain dialogue generation on the Khan VAI2 dataset. It uses several text quality metrics, like the Bilingual Evaluation Understudy, or BLEU, which scores generated text against a reference, and scores from bidirectional encoder representations from transformers, or BERT, assessing similarity through F1, precision, and recall. For Llama 3 to 8B, Hadamard high-rank adaptation with R equals 32 achieved an average score of 47.80%, clearly topping DORA's 46.62%. Impressively, even with fewer parameters, Hadamard high-rank adaptation is still very competitive. Okay, so after looking at dialogue, this next table shifts focus to mathematical reasoning, specifically on the GSM 8K benchmark, which tests grade school math word problems. We're again comparing different fine-tuning methods on the Llama 3 to 8B model, and it's a similar story of strong performance. Hadamard high-rank adaptation with R equals 32 scores a notable 70.81% accuracy. This result is quite a bit better than LoRA, which achieved 67.98%. What's also interesting is that Hadamard high-rank adaptation with R equals 16, using fewer parameters, still performs very competitively. So across these diverse tasks, from common sense reasoning to dialogue and math problems, we've consistently seen Hadamard high-rank adaptation come out on top. The key seems to be its clever use of the Hadamard product, that element-wise multiplication with the original pre-trained weights, which allows for a more expressive, higher-rank update to the model. This really boosts adaptability without sacrificing parameter efficiency. That's all for this AI Research Roundup. Thanks for tuning in.